All right, today's lesson or this video we are going to talk about shifting equilibrium, which is section 2 in chapter 11. Uh, the shifting equilibrium would be changes in pressure, concentration, or temperature can alter the equilibrium position and thereby change the relative amounts of reactants and product. So we have to talk about some points where the reactions or equilibrium reactions can change. And that is due to the Chatelier's principle, which says that if a system at equilibrium is subjected to a stress, the equilibrium is shifted in the direction that tends to relieve the stress. So, for example, if a system is already at equilibrium and there is a change or there is a stress by changing concentration, pressure, or temperature, how would the reaction react? How would the reaction with change shift in a direction to relieve that stress? So we have categorized those changes, those shifts, into three parts. First of all, it's changes in pressure. Changes in pressure, uh, when we talk about change in pressure, we can talk about change in volume as well, especially for gases. Pressure and volume are inversely proportional. For example, if you increase volume, it means that you are decreasing pressure. Increasing volume, decreasing pressure, or vice versa. By decreasing volume, you are increasing pressure of a gas system. This system, as we said before, it only affects the systems which contain gases. And there is a very good point, a very uh, important point in this area, and that is uh, for a reaction or for a change in pressure to be effective, it has to be the total number of moles of gas on the left side of the equation must be different from the total number of the moles of gas on the right side. What does that mean? If two sides of the equation has the same number of moles of gas, changes in pressure has no effect on that equilibrium state. Uh, if we look at this reaction for an example, which is Haber process, uh, this reaction has 4 moles of gas on the reactant side, while 2 moles of gas on the product side. So if the reaction or if the question asks what happens if we increase pressure on the system, you have to look at the number of moles of gas in each side of the reaction. For example, if we increase pressure, if you look at the points here, if we increase pressure or volume decreases, both of them are the same, because sometimes in questions, instead of saying pressure increases, it will just say volume decreases. We can say equilibrium states shifts in direction towards the fewer mole. So from higher mole towards the fewer mole. But if pressure is decreased, like this one that is talking about, if pressure is decreased, then the equilibrium state shifts to greater number of moles towards the side of the greater number of moles in the reaction. So for example, for this reaction, if we increase pressure, for example, let's say P increase. So what will be the direction of the shift for this particular reaction? The direction of shift will be forward because the reaction has to relieve the stress that is produced in that area. But vice versa, if pressure on this system, if pressure, sorry about that, if pressure is decreased on this system, like this, the direction of shift would be towards the reverse direction. So as you can see, I have looked at the number of moles of gas in both sides, in the reactant side and in the product side. Since in the product side we have 3 and 1 here, so in total 4 moles of gas, while in the product side we have only 2 moles of gas. So the direction of the shift by increasing pressure would be towards the right side, from higher mole of gas towards lower mole of gas. The same can be applied for this system of reaction, as we have seen it before in chapter 1, where it talks about dissolving a gas inside a liquid. for example, by dissolving CO2 in H2O, the CO2 would react with H2O, forming carbonic acid. And as you remember, by increasing carbon dioxide, or by increasing concentration of carbon dioxide gas, the solution was higher, the solubility was increased, thus more CO2 was dissolved inside the H2O. So the reaction would be shifted towards the right side. So for this reaction, particular reaction, yes, we only have one gas. So we can say that uh, the reactant side contains only 1 mole of gas. Only 1 mole of gas. So here it's only, sorry about that. So we only have 1 mole of gas here and 0 moles of gas on the product side. So as you can see, it's in aqueous state, while this one is only 1 mole of gas. So by increasing pressure, the direction of the shift will be towards the right side, while by decreasing pressure, the reaction will be towards the left side, just like we studied in chapter 1. The introduction of an inert gas. What do you mean by inert gas? A gas that is not present inside that reaction. A gas that is not a reactant nor a product, such as helium or any other type of gas that is, for example, let's say xenon or argon or let's say krypton or neon. And none of those gases, by adding any of those gases, none of them would have any effect on the pressure, on the pressure of the partial pressure of the gases that are present inside that reaction. So that they won't affect the equilibrium state of that reaction. All right. So that was the changes for pressure on a system. Now let's get into changes in concentration. What would happen if there was a change in concentration in a reactant or a product? Uh, you can think of it like this. By changing concentration of anything, the reaction will shift towards the other side. What do I mean by that? I mean, for example, if I increase concentration of A, of reactant, which is a reactant, the direction of the shift will be to the right, to forward. But by decreasing concentration of any substance, the direction of the shift will be towards itself. For example, if I decrease concentration of A, the direction of the shift will be to the left. So again, if I increase concentration of A, then the direction of the shift will be to the right. But by decreasing concentration of A, the direction of the shift will be to the left. Then what happens to the other substances? So when I say what happens when we change concentration of A, we change the concentration of A. That's the stress. So think about the other points. Now, let's not look at A for now. When you know that by increasing concentration of A and the reaction has shifted to right, let's look at B. Since B is left behind and B is used and it's just behind the arrow, so B, the concentration of B must decrease. But since C and D would be just right behind the arrow like this, then both of the concentration of C and D would increase. So the same thing's written here. An increase in concentration of A creates a stress. So to relieve the stress, some of the added A reacts with B to form products C and D. Now this is the change of the concentration of A, B, C, and D. So the equilibrium is reestablished with a higher concentration of A, of course, because we have added some A, and some of that A is passed towards the product. So some of them is left. But the concentration of B would decrease. As a result, the concentration of C and D are also increased. The only thing that is changed is B, or that is decreased is B. What if we change the concentration of another thing? Let me give you an example like that. For example, if we increase concentration of D, let's say, less concentration of D, sorry about that. All right, if concentration of D is increased like this one, let's delete this one. All right, what happens to the concentration of C, B, and A? So by increasing concentration of D, you are increasing concentration of A and B. Why? Because some of that D, the direction of the shift will be to the left. The D is transferred, some of that D is transferred back to A and B. So some more A, some more B are produced. But what about C? Then C would decrease. Why? Because by increasing D, the reaction will shift to the left. So some of that C is used again to produce again A and B. So the concentration of A and B are increased while C is decreased. So if we want to know what happens after we change concentrations or changing concentrations on an equilibrium system, will it affect the equilibrium constant, which we mean K? No. By changing pressure or concentration, the value of K will not change at all, because the change in equilibrium would be in a way that the numerator and the denominator would have the same ratio that was in the previous one. I'm going to show you some examples later so that you can see that no K is changed by changing the concentrations. Uh, but when we talk about concentration, you have to be very careful that we talk about aqueous solutions and gas reactions or gas substances. Having pure solids and liquids, since we didn't care about the concentration because the concentration are very high and they don't change, they remain constant. That's why changing concentration of solid and liquid would have no effect on the equilibrium state. Changing concentration can be used in various ways in uh, equilibrium states. For example, by removing or by decreasing concentration of a product or by removing a product, you can make the reaction to go forward in a continuous way, such as in Haber process. So you remember Haber process in here. Imagine we constantly remove NH3 by liquefying the NH3, making it to liquid. If we constantly remove NH3, it means that we are decreasing concentration of NH3. Then the reaction will shift forward. As we said, if something is decreased, the reaction will shift towards itself. So the reaction will shift forward. But on what expense? It would be on the expense of using nitrogen and hydrogen. Those two will be used up in order to make more NH3. Again, we will remove NH3 again, and those two will react again to form NH3 for the second time. Let me give you an example. For example, let's say this is just hypothetical. NH3 at equilibrium is 100 molecules, and nitrogen and hydrogen are 100 molecules. So by removing 50 molecules from the all 100 molecules of NH3 from the reaction, so these two reactions must produce another equilibrium state. So the 100 that was here will be divided to two parts, 50 here, 50 again there. Now the reaction has decreased to a lower equilibrium. Again, remove the 50 molecules that is produced due to the stress. Now the 50 removed here, 50 is left here. Now that 50 will also be divided and so on and becomes 25, 25, and so on until we make the reaction to react all the reactants and make products. So that was a way for removing a product and making it to give it all the reactants or to change all the reactants towards the product. So these are the rules that we talked about. Now, another example. You remember this reaction from self-ionization of water, which water basically ionizes, self-ionizes to form H3OH, and the concentration of both of them multiplied would be 10 to the power of negative 14 at 25 Celsius. So if you remember, by increasing concentration of H3O, concentration of OH decreased, and vice versa, by increasing concentration of hydroxide, the concentration of hydronium decreased. Why is that? Let's apply to the same rules that we have studied here. If we increase concentration of OH, reaction will shift to the left. So what would happen to hydronium? Of course, hydronium would decrease, and vice versa. For example, let's say if concentration of H3O is increased and concentration of OH is decreased, the direction of the shift will still towards the left side. Thus, by increasing H3O, the reaction will shift to the left. Using hydroxide, that's why the concentration of OH would decrease. Why? So that the Kw would remain as 10 to the power of negative 14. All right, 10 to the power of negative 14. Now, for another reaction. In this reaction, if you want to change concentration, the only thing that can be changed is CO2, because this is the only one that is gas, but the other ones are solid. And we know that concentration of solids don't change. So if we want to change concentration of CO2, by increasing CO2, the reaction will shift to the left. By decreasing CO2, the reaction will shift to the right. But bear in mind that concentration of K, or the value of K will not change at all. All right. Now, all right, let's continue. Now let's get to changes in temperature. Reversible reactions are exothermic in one direction and endothermic in other. So every reversible reaction, if it's exothermic in a certain direction, the reversed reaction or the other reaction would be endothermic. And the effect of temperature cannot be directly explained. It has to be known that if the reaction is endothermic or exothermic. According to Le Chatelier's principle, the stress of the added heat will be lessened by shifting the equilibrium in the direction that removes heat. We'll get into that later in a minute. What do you mean by that point? So, in order to know that what happens when you increase temperature or decrease temperature in a reaction, we have to know first of all that the reaction is exothermic or endothermic. So for exothermic reactions, if temperature is increased, so for example, this reaction is exothermic reaction. If temperature is increased, you are applying heat to the product side of the reaction. So you are forcing the reaction to go back to the reactant side. So the reaction will favor the reverse reaction or will shift to the left. But here's the point. K now changes by changing temperature, and K will decrease. So by increasing temperature, but this is only for exothermic reaction. So if I may write a point here, we can say that temperature is directly proportional to K. Inversely proportional towards K. So by increasing temperature, since the reaction will shift to left, so K decreases. But by decreasing temperature, the reaction will shift forward. Look at this point here. Let's just undo this. undo those. All right, not a problem. Good. All right, now here we go. As I said, changing temperature for exothermic reaction is inversely proportional with K value. Why? Because due to the reverse and the forward reaction. Why? Because since you don't add any concentration to this point or to any of those reactions, then by changing temperature, you are forcing the reactions to go back to fourth or reverse direction, thus the reaction will change. All right, increasing temperature, for example here, will decrease NH3. By increasing temperature, the reaction will shift to the left. So if the reaction shifts to the left, the NH3 will decrease, hydrogen will increase, nitrogen will also increase. Thus, you are decreasing product and reactants are increased. So K will decrease because NH3 is the product. But there's something about ammonia, by production of ammonia. That reaction must be at high temperatures because at low temperature the reaction will be too slow to be commercially useful. So for the reaction for production of ammonia would have to be around a moderate temperature about 500 Celsius. But by increasing that amount of temperature, which is 500 Celsius, the reaction will shift to the reverse side and ammonia cannot be produced. Then how can this problem be solved? Since the reaction cannot be done in low temperatures and we want to make ammonia, not decompose ammonia. So the reaction has been solved, or that problem has been solved by increasing pressure. How is that? Because if you look at the reaction, there are 4 moles of gas on the reactant side, while only 2 moles of gas on the product side. So if you go back to the first change in concentration, about pressure, you can see that if we increase pressure, the shift or the relieving of stress would be from higher mole of gas towards lower mole of gas. That's why a satisfactory amount of ammonia can be yielded or produced. There's another example for changing temperature and how would it affect on a reaction. We have this reaction, NO2 can be changed to dinitrogen tetroxide in a reversible reaction in an equilibrium system. But the reaction, the forward reaction, is exothermic reaction. So by increasing temperature, you are shifting the reaction towards the left side and concentration of dinitrogen tetroxide would decrease and concentration of nitrogen dioxide would increase. So since I have written brown and colorless here, if we increase temperature, you are forcing the reaction to the left side, so you are making more nitrogen dioxide, which has a brown color, and vice versa. By decreasing temperature, the reaction will shift to right, and more dinitrogen tetroxide will be produced. Look at this figure here. This explains a lot of it. So look at 0 Celsius. At 0 Celsius, if you compare it to the reaction at 0 Celsius, which is decreasing temperature, the reaction will shift to the right, a more colorless substance, which is N2O4, will be produced. But as temperature has increased, the reaction has shifted to the left, more brown is produced. As you can see here, the system shows more brown color has been produced. And of course, K or equilibrium constant would change accordingly. What about for endothermic reaction? All we said about exothermic reaction would be correct. For endothermic reactions, if temperature is increased, look at here, you are forcing the reaction to go to forward reaction or shift to the right. By shifting the reaction to the right side, K would increase. So you can write here K increases. Increases. And at the same time, for this one, if temperature is decreased, the reaction is reversed, so K decreases. All right, as we mentioned before. So that was for endothermic reaction as well. There's one point that hasn't been mentioned specifically, but I have written it as of the fourth change in an equilibrium system, which is adding a catalyst. So adding catalyst has no effect on the equilibrium system whatsoever. What do you mean by that? It doesn't affect the amount of product or reactants or any shift. It only speeds up the reaction. It increases the rate of the reaction that reaches equilibrium state. I have added a question here to predict the shifts. So the reaction says, or the question says, predict the effect of each of the following on the indicated equilibrium system in terms of the direction of equilibrium direction, forward, reverse, or neither. Value of K, increase, decrease, or neither. For example, here, by increasing NH3. So this is NH3. If we increase NH3, the reaction will shift to right. If it shifts to right, what happens to K? So K doesn't change. What about this one? Removing HCl. So removing HCl, as you can see, by removing something, the direction of the shift will be towards itself. So the shift will be towards left side. What about K? Of course, K doesn't change as well. Adding helium gas. Adding helium gas is an inert gas. And if you remember, inert gases, adding inert gases on a system which does not contain that gas specifically, so no change at all on the equilibrium system. Adding NH4Cl. Some students get confused at this point. If we add NH4Cl, since it is solid, and concentrations of solid don't change. So don't get confused. Don't make that mistakes. It doesn't shift towards any side, so no change because it is solid. What about increased pressure? We have to count the number of moles on the reactant side and the product side. For example, for here, you can see that 2 moles of gas in the reactant side, while in the product side, 0 moles gas is present. So the direction of the shift will from the higher mole of gas towards the lower mole of gas. The direction of the shift will be forward. What about increased volume? If you remember, we said increased volume is inversely proportional with pressure, or volume is inversely proportional with pressure. Increased volume means decreased pressure. So if increased pressure is forward, then increased volume or decreasing pressure will be in the reverse direction. Adding a catalyst, again, adding a catalyst will have no effect on the reaction, only speeds up the reaction, increased temperature. So until this point, no change or no stress has changed equilibrium constant. But what about temperature? So the reaction is exothermic. By increasing temperature, the reaction will shift to the left. All right, now it's shifting to the left. What about K? What about equilibrium constant? Shifting the reaction towards the left side means that more reactants have been produced. The value of reactant have increased, and the values of reactants, when increased, then K must decrease. So that was for this reaction. That is the changing of equilibrium. There is a question in chapter review, question 47, which is kind of related to this point and also related to section 1. So I have added the solution here. First, you have to find something that's called Q. What is Q? Q here is the ratio of product to the ratio of reactant, but at any other point than equilibrium. So for this reaction, if you have the question here in front of you, you can see that K is 0.01. Now, we have some amount of more amounts of moles or different amounts of moles other than at equilibrium of these substances. I have found Q. Q tells us if the reaction is at equilibrium or not, or there is more product or there is more reactant. As we have calculated Q we got 0.016, which is bigger than equilibrium constant. It means that the reaction is still not at equilibrium. So higher number of Q means that the products are higher, the reactants are lower. So if the products are higher and the reactants are lower, what would the reaction do? Or what side will it shift so that the reaction will go back to the equilibrium state? So of course, if Q is bigger than K, this is a general rule, always the reaction shifts in the reverse side. But if you have another question and Q is smaller than K, then reaction shifts forward, not in the reverse direction. But if Q is equal to K, then the reaction doesn't have to do anything, and the reaction is already at equilibrium.